So here we have another Calculus 2, locally we call this Math 166 exam. This one is from spring 2023. And I'm sure, like all Calc 2 exams, it's going to be a lot of fun, meaning algebra, algebra. And, well, anyway, so something to look forward to. But don't worry, you can do these tests. You can succeed. With practice and hard work, we will get you through this test, or my name is not Reginald Q. Picklebottom. And with that, we can put our name down. Don't forget. And you might say, wait a second, that's not your name. Well, we'll just put solutions, and off we go. Number 1. Consider the curve given by the parametric equations. X is cosine t, y is t plus sine t, and t goes from 0 to pi. Set up, but do not evaluate. Integrals expressing, then we have parts A and parts B. And I will say, this is one of our favorite phrases on a Calc 2 exam. Do not evaluate. So this is about setting things up. Do we know how to put the formulas into place? And a lot of the challenge in this type of exam is the setup. So don't skip that. That's probably the most important thing. More points on this exam will go to setting things up than they will go to integrating. So take your time. Don't skip anything. All right, so let's look at part A. We want to do the length of the curve from time 0 to pi. Well, sure, all right. Now, what do we have? It's parametric. Now you might say, well, how do you know it's parametric? Well, it told us. That's a pretty solid clue. But we also can see it's parametric because x and y are functions of t. Now the reason I mention this, and I'm like emphasizing parametric, is there's actually several different formulas for arc length. It depends on how the curve is being described. There's y as a function of x, there's parametric, there's polar. So you want to make sure you're using the right formula. Now for parametric, what do? Well, you're going to add up, and so that's what an integral is. It's adding things up, start to finish, and then you're going to have your little bits of length. And that's, very, very simplistic. So small pieces of length. Now for parametric, what that formula for length becomes, it's the square root of x prime squared plus y prime squared dt. All right, so that's our formula. So what do we need to do? We need to find x prime, we need to find y prime. We know our start and stop. It's given to us 0 and pi. All right, so let's do some computations. X prime, the derivative of cosine, negative sine. Y prime, well, 1, and the derivative of sine is positive cosine. And so we can say our answer is the integral 0 to pi of the square root of minus sine t squared plus 1 plus cosine t squared dt. And that's a valid answer. And you might say, well, wait, didn't we need to simplify? Hold on, let's grab our cover sheet. Remember, you do not need to simplify unless indicated. So that's a nice fact to remember. However, I do like things being simple. So let's go ahead and simplify it a little bit because, why not? We're here, the test is here, let's all have a good time. So to do the simplifying, what we would do in this case is say, all right, let's look inside that square root, because that's where all the complicated things are happening. So here, what would we have? So this piece would become, well, we have sine squared, all right, and now we square that. Well, that'd be a squared, 1 squared, 2ab, 2 cosine, b squared, cosine squared. And we always say, well, sine squared and cosine squared, classic, beautiful formula, it's 1. And then there's another 1. So altogether, there's 2. and then 2 cosine t. So we also could have said integral 0 to pi square root of 2 plus 2 cosine t dt. And this would also be correct. They'd both be correct. And so there we go. So that's length. Now this is just part A. Of course, we have part B yet to come. All right, so let's take a look at part B. They didn't give us a lot of space here, but what do we have? The surface area obtained by revolving the curve around the x-axis, where time goes 0 to pi. All right, well, what do we have? Well, it's a little hard to figure out exactly what our curve is doing, so let's just pretend like we kind of have a vague idea. Maybe it's doing something like that. Okay, so here's our curve. It doesn't really matter exact. Now, where are we revolving? Around the x-axis. Remember that. We'll come back to that in just a second. And so we're going to spin. And when we do that, well, we're going to form a shape. And, well, we're after the surface area. Now, we think about finding things by thinking about small pieces. That's the whole idea of calculus. Break things into small parts. You understand each small part, and life is good. So for surface area, what do you have? Well, what you do is you add up, that's the integral, from start to finish, and then you have a 2 pi, a radius, and length. Now, we should explain, where does the radius come in, where is length? So what we're doing is we're saying, well, you chop up. So this is your little segment, and you spin it around, and it's a little bit of a ribbon here. And so the length is this part. That's length. And now, what's the radius? Well, let me switch colors so that we can illustrate that. I happen to have more colors. What are the odds? Steve has lots of pens? Yes, it's true. So radius is how far down to where we spin. All right, so that's an important thing to remember. Now, we say, okay, do we know A to B? Yes. 0 to pi, given to us. Great. Do we know length? Yes. That's what we just found up here. Great. Do we know radius? Now this is where we have to pay attention. So we're going around the x-axis. So around the x-axis, you say, okay, if I have a point here, x comma y, what's the distance down to the x-axis? Why? Well, because we need to know, right? No. It's the y value. So the y value gives you your distance. Now, here's the point where there's a small technicality that we're just going to take 30 seconds because we're pros at this and we don't want to get tricked. It's technically the absolute value of y. Well, because y could be positive or negative. So you want to take a quick peek and say, okay, could t plus sine t be negative? Well, it turns out it can be if you choose the right values of t. But between 0 and pi, t and sine t are both non-negative. So when you add them together, they're both non-negative. So we don't need to worry about absolute value. Now, I believe that your calc teachers are good, kind people, so that they never do that to you. But I'm just pointing this out because, you know, life happens. And if you're ever walking down the street and someone says, hey, wait, I need you to compute a surface area. You're like, I got you. And you'll know all the subtleties. Okay, so here we go. It's more or less the same integral. We just need to add in these extra pieces. So we're going to have 0 to pi. We throw in our 2 pi. We throw in our radius y, which remember is t plus sine t. So t plus sine t, and so we'll add that in. T plus sine of t. And then the length, that's this whole piece right here. So that's the square root, and we'll use the short version. If you use the long version, that would work too. And there we we go. Life is good. One problem down. Number 2, draw a line segment connecting each Cartesian equation on the left. So Cartesian involves a formula, x and y, there's an equal sign somewhere, with its corresponding parametric equation on the right. And well, this is interesting because it turns out there's oftentimes many possible parametric equations for a single Cartesian. And so it's kind of a little bit of misdirection here, because it's making you think, okay, let me start here and go to there. When actually it's easier to start here and go to there. Because what's going on? Well, what happens is that we have an x of t, y of t. That's what we have when we talk about parametric. And so what we can do is we can just say, all right, suppose this is my x and this is my y. I plug it in, and is it true? So does cosine t minus 1 plus sine t equal 2? No, no, no. All right, how about does sine t equal cosine t over cosine t minus 1? No, it doesn't sound like a trig identity. Well, does cosine t minus 1 plus sine t equal 1? No, 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 no. This is not looking very good. 1/4 x squared plus 1/9 y squared equals 1. Well, the problem here is when you square this, you're going to get a minus 2 cosine t, and there's no way to compensate. And then we come to this one. X squared plus 2x plus y squared equals 0. Well, we've kind of eliminated this. And, well, does it work? I think it does. Let's just check. Notice this x squared plus 2x plus y squared. You could say, well, if you almost have a perfect square going there at the start, let's make it a perfect square. Add 1. And then, of course, you have your y squared. Now, if I add 1 on the left, I balance things out, so there's 1 on the right. And then I haven't really changed anything. So this becomes x plus 1 squared plus y squared equals 1. Now, look at this. If I take cosine t minus 1 and add 1, that's cosine. So cosine squared plus sine squared, does that equal 1? Yes. So that says these match up. Now, you might say, oh, wait, was it straight enough line segment? Don't worry. They're not going to pull out a ruler and say, oh, there's a slight bend here. That's not going to work. Just make sure it's pretty straight, and also make sure it's unambiguous. That's the only thing you need to worry about. Okay, let's go to our next one. We want to have it that when we add the x and the y coordinate, we'll just see here. Here's x, here's y. If I add x and y, do I get 2? Right? T plus 2 minus t. Does that equal 2? Yeah. Well, that was quick. Ba-dum! Nice. Cool. Well, all right. What happens here? All right. We have t squared and 1 plus 1 over t squared. All right. Well, if I take t squared plus 1 and divide by t squared, is that the same as 1 plus 1 over t squared? Well, yeah, right? Because this is really, think of this, look at this. This is really t squared over t squared. So it's t squared plus 1 over t squared. So, so that matches. Okay, great. So remember, we're taking this and plugging them into the formulas, and we're seeing, does it work? So that's it. Don't start here and try to get there. Hopeless. Start here and say, does it satisfy the relationship? And then it's just like, yes, no, and then you can quickly figure it out. All right, now 2 left, and let's see. Here, remember this is x, this is y. Does 2 sine t plus 3 cosine t equal 1? No, hopeless, hopeless. How about here? All right, square x, that's 4 sine squared. Divide by 4, so that just becomes sine squared. And then we have 9 cosine squared, over 9 is cosine squared. So it becomes sine squared plus cosine squared, which is 1. Aha! That matches up. And now, by process of elimination, well, there's only one more chance, right? And, okay, if this is x and this is y, x plus y, does that equal 1? Yes, it does. And there we go. That's it. That's the process. It's not so bad. You just have to think about what's going on and how to test. And it's much, much easier to go from parametric to Cartesian than the other direction. All right, so now we have 2 down. Woohoo! Number 3. How much work does it take to lift a 100-pound person 10 feet in the air if the rope being used has a weight density of 2 pounds per foot? Now, before I start this problem, if you're a physics person, you're probably saying, hold on, you've left out important information. And that's true. I will honestly say this problem did leave out important information, and it's making you make an assumption. And this is not me trying to say, oh, the test writers, God, they should have been a little bit more careful. But I will say in this case, they should have been slightly more careful. But that's okay. I love those test writers. They're wonderful people. So what's the piece of information that is kind of missing here? And they want you to make that assumption. Well, namely, the question is, how much rope is there? Because you could imagine that you have a piece of rope that's just exactly 10 feet up. And so your pulley is something like this. So here you are pulling your rope, and it's, well, that's a very short person for 10 feet, but okay. And that's a very different situation than if you were, say, 100 feet. Because you can, in both cases, lift something up 10 feet. But it's very different because here you have a lot more rope that you have to actually pull on, whereas here you have less rope that you have to pull on. But let's just give them the benefit of the doubt and say, okay, this was it. This is our setting. Okay, so what's going on? Well, it's a work problem. How do you do work? Well, work is done by adding up force times distance. And the usual way we think about distance is just a small change in height. So we have this heavy weight, and in this case, the heavy weight turns out to be a 100-pound person. We say, okay, so we're lifting that person up, and how much does it take for us to move that little amount? So let's suppose we label this as y, and now we have to, whenever we're doing a physics problem, we have to make a choice when we put units. Where is 0? Do we put it down here, or do we put it up there? And the answer is, yeah, wherever you want. And honestly, they both work. It's just a matter of saying which one is more convenient. And I will put it up here. So here's y equals 0. Here's y equals 10, down there. All right, so now what's happening? Well, I need to say, what's my work? I'm going to move it between 0 and 10. Okay, adding that up. My force, well, I always have the 100 pounds. So there's 100 plus, and now, this is where the picture comes into play, I have to account for the weight of the rope. Because I'm not just pulling up the person, I'm pulling up the rope, because the rope has weight. And namely, it weighs 2 pounds per foot. So if I'm at a height y, and remember this is from 0 to y, so that's y, well, how much does that rope weigh? Well, it's 2y. So you notice that y equals 10 feet, right? Because that's on the ground. There's 20 pounds of rope to be lifting, whereas once we hit at the top, well, there's no rope for us to lift. Okay, so it's 2y. What's the distance? So this is force. The distance, dy. So that's the setup. All right, good. Now, all right, we're not in that setting. So what do we get? you get 100y plus y squared. Evaluate 0 to 10. And, well, 100 times 10 would be 1,000. And then 10 squared would be 100. And so we get 1,100. Okay. Are we done? Yes. Could we do anything else? Sure. The other thing that we could do is actually work through and say, what are the units? And this we can figure out by looking at the problem and getting context and just knowing what kind of units get used. In this case, we have our force is a pound measurement. Our distance is a foot measurement. And so we could put in foot-pounds. Now, sometimes they will say include units. Sometimes they don't specify. If they don't specify, you don't have to put them in. But if they say to include it, make sure you put them in. But for us, 1,100, that's the amount of work. And now we're done. Nice. Woohoo! Number 4. A solid lies between planes, perpendicular to the x-axis at x equals 0 and x equals pi over 2. Okay, all right, interesting. And so what that's saying is x equals 0 is here, x equals pi over 2 is here. All right, so it's just saying it's in between those two. And now, when we take a cross-section perpendicular to the x-axis, so a typical cross-section, it looks like an isosceles right triangle with the hypotenuse running from the x-axis to the curve y equals sine x. Okay, so there's our figure. I'll tell you, as figures go, beautiful figure. And now what are we trying to do? Well, we're trying to find the volume of the solid. Okay, interesting, interesting. Now, what do we do for this kind of problem? Well, in this kind of problem, what we can think of doing is actually think of taking sort of a little bit of a thicker slice, not a very thick slice at all. So we'll say that the width here is dx. You'll notice that our cross sections aren't circles, they're not shells, they look like thick triangles. So this is one of our basic formulas, namely that our volume is adding up start to finish. Then we do an area of our cross section and our little bit of width. So the width here is our dx. So the hard part about this problem is going to be the area. And then we're actually going to have to integrate because it's not setting up, it's finding. And so we say, oh, okay, all right. We can do this. So let's think about what's going on. Let's take our triangle and draw it a little bit more friendly. We have to know some words here. We know the length of the hypotenuse because we're told the hypotenuse sits here going from 0 to sine x. So this length is sine of x. We also know that it's a, where would we have it? It's an isosceles right triangle. So that's why I put a right angle there. But I just copied that from the picture. To be isosceles means that these are pi over 4 or 45 degrees, whichever one makes you happier, in both corners. Okay. Now, the question is, what's the area? Now, the way we normally find area is it's 1/2 base height. But we don't know the base and we don't know the height. We know the hypotenuse. So let's just step back for a second and say, all right, well, if I have this kind of triangle, and I have that this is length A and this is length A, because it's isosceles, these lengths are going to be the same. Well, this length will be, well, a squared plus a squared, and then take the square root. Pythagorean theorem, right? This squared plus that squared equals that squared. And so this has to be the square root of a squared plus a squared, which, well, turns out a squared is a, and you end up with square root of 2 times a. So our great aha says, oh, if sine of x is the square root of 2 times the length, then what we can do is say that our lengths on these two sides are sine of x over square root of 2. Right? That's, well, see, because again, sine of x is square root of 2 times a, so a you divide. So sine of x over square root of 2. Now, we can say that the area, and well, I'm running out of space here. All right, we'll put this down a little bit. So this area is 1/2 the base times the height. They're both sine x over square root of 2. Well, square root of 2 times square root of 2 would be 2 times 1/2, which gives you 1/4 sine squared x. There we go, 1/4 sine squared x. Now we're ready. We've done the hard part, but of course we still have plenty left to do. So we're adding up 0 to pi over 2. So those are our bounds. Our area, 1/4 sine squared of x, and our width is our dx. Now, how does one go about integrating sine squared? Well, we don't do it right away. We write it. Very common thing we do with trig, because there's so many identities. And there's something called power reduction. So we can take sine squared and make it look like something without a square. And in particular, we say, oh, well, this is the same as 1 minus cosine 2x over 2. One of our classic trig identities. All right, well, we have a quarter and an over 2. We can pull that out as a 1/8 integral 0 to pi over 2. And we have 1 minus cosine 2x. All right, so that becomes 1/8 integral of 1 is x, then minus, well, integral of cosine is sine. And so it'll be minus sine, right? So integral of cosine is positive sine. And, you know, they are very picky, so make sure you get the right thing. And so also remember, when you integrate, you have to account for the 2. Now you can do it in a few steps and say, okay, u equals 2x, du, blah, blah. Or you can just say, you know, I've seen this so many times by now. I know that the way I account for that 2 is put in 1/2 and evaluate from 0 to pi over 2. Say, all right, plug in pi over 2. Well, what do we have? 1/8 pi over 2. Then we have sine of 2 times pi over 2. Sine of pi is 0. Okay, 0. Great. And we'll subtract. Now plug in 0. Well, 0 minus 1/2 sine of 0. Sine of 0 is 0. Ah, wonderful. Lots of zeros. 0 is a good friend. We like it when we get a lot of zeros. So what do we end up with? 1/8 times pi over 2, also known as pi over 16. And we don't have any units, so that's just it. Pi over 16. There's our final answer. Nice! Cool. Geometry. Gotta love it. Gotta love it. Number 5. Let R be the region shaded in the figure below. Ah, there you are. Hello. Which is bounded by the lines y equals 1, y equals 2x, y equals x squared. Use the method of cylindrical shells. Now, notice how they bolded that? It wasn't just enough to say it. They were like, ah, ah. They really wanted us to see that. Now, what they're doing here is they're saying, you have to use the method we tell you. So if we used some other method, we wouldn't get points. Well, maybe you'd get like a pity point or 2, but not enough. Our goal is, gotta get them all. We want all the points, right? So we're gonna make sure to follow the instructions. And we want to find the volume of the solid generated by revolving the region R, that's the shaded region, about the line y equals minus 1. All right, so first off, let's start by sketching y equals minus 1. So I know this is feeling a little bit sketchy. All right, but we should sketch it. Okay, so let's say this is y equals minus 1. So this is where we're revolving around. Now, what are we trying to do? We want the method of cylindrical shells. So there's a question that we always ask ourselves, which is, how are we slicing? So we could slice our region in two ways, vertical slices or horizontal slices. Now, if you had a vertical slice and you took that and you spun it, what shape would you be forming? It would be a washer. Well, that's not a shell. So it's telling us we better be doing our horizontal slicing, because with the horizontal slicing, when we spin, we're going to be forming indeed what we need, which is we're going to be forming our shells. All right, good. Cool. All right, so now we know how we're slicing. And we also have been just told in a very subtle way that says, oh, since you're doing horizontal slicing, we're really going to talk about integrating with respect to y. All right, so let's recall, how do cylindrical shells work? So the volume is you're adding up start to finish. We have 2 pi, a radius, a height, and a thickness. All right, so those are our things. Now you'll notice here, radius is a distance measurement, height is a distance measurement, and thickness is a distance measurement. So it really is a proper volume type idea. Now the thickness, that's not so bad. We can talk about that really quickly. That's going to be, this little piece right here. So this is dy, a small change in y. All right, that's our thickness. Easy, easy. What's the radius? Well, the radius is going to be from our slice down to where we're spinning. Now, what we have is we're integrating with respect to y. So this is y. So how far is it from y down to the line y equals minus 1? Well, we would take y, subtract minus 1. So our radius is y plus 1. If you like, you can think of y down to here, and this is another 1 further down. All right, so now we have our radius. What's our height? Well, our height corresponds to this portion. So here's our height. And we should have marked radius, so let's just do that right now as we pay attention. And you're probably thinking, my goodness, do I need to bring in this many colors for the exam? It's up to you. Bring in whatever you need. 1 or 2 isn't bad. But all right, so how do we find this? Well, the key here is we need to make sure that we have things in terms of y, because we're integrating with respect to y. That's what the dy tells us. So on the left-hand side, we want this as a function of y. So we're going to solve for x. So we say, look, x is 1/2 y. And on the right, we say, all right, what's this one? Well, if y equals x squared, x is positive square root of y. Negative square root of y would be this part of the parabola. Now, when we're looking for height, we take high value minus low value. So it's either top minus bottom, or, because we're horizontal, right minus left. So we're going to take square root of y, high value, subtract 1/2 y, low value. So this part is square root of y minus 1/2 y. Now, one more thing, which is the bounds. The bounds, let's not forget the bounds. And how do we do that? Well, again, look at y. We need to say, where does y go from? We see our lowest value for y is right down here at 0, and our largest value is at 1. So we're going to go 0 to 1. All right. Whew. The hard part's done. Now it's just finding the answer. All right, good. So off we go. Let's rewrite this. So we need to do the integral 0 to 1, 2 pi, y plus 1. Now square root of y, I like to write anything with a square root in a calculus-friendly way. And when I say calculus-friendly, I mean with the rule. So y to an exponent, y to the half minus 1/2 y dy. All right, well, okay, we have to find it. It's not just a setup problem. So we can pull the 2 pi out, and now we just carefully work it through. Y to the 1/2 times y is y to the 3/2 y times y minus 1/2 y squared. That's that part. 1 times y to the half is y to the half. 1 times minus 1/2 y is minus 1/2 y. All right. And the good news is each one of these integrals is a nice one, right? You know, when they ask you to find things, they tend to not be integrals that are too bad. Okay, so what's the rule? So it's always y to a power. So the rule is add 1 to the exponent, then divide by that exponent. 3/2 plus 1, 5/2. So we're going to have y to the 5/2. But then multiply by the reciprocal, or divide by the exponent. So divide by 5/2, same as multiply 2/5. Okay, y squared will become y cubed. Divide by 3, same as multiply by 1/3. It's already a half, so that's minus 1/6. Y to the 1/2 becomes y to the 3/2. Divide, which is same as multiply by the reciprocal, and so there's a 2/3. Y to the 1 becomes y squared, y to the 2. Divide by 2, so we end up with minus 1/4 y squared. Evaluate 0 to 1. Now the good news is 0 is easy. You get 0, 0, 0, 0. And the other good news is 1 is easy, because y, 1 to any power is 1. Okay, so we have 2 pi times 2/5 minus 1/6 plus 2/3 minus 1/4. And now, well, we're almost done. Okay, what's something that is divisible by 5 and 6 and 3 and 4? 60, right? Yeah, 60 works. Okay, so let's do that. So we have 2 pi, and now we have everything over 60. So, okay, what do we need? To get 5 up to 60, you multiply by 12. So 2 times 12 is 24. To get 6 up to 60, you multiply by 10. So that's minus 10. To get 3 up to 60, multiply by 20. So there's a plus 40. And to get 4 up to 60, multiply by 15. So that's minus 15. All right, so that's just putting everything over 60. All right, so we have 24 minus 10 minus 15. Actually, minus 10 and minus 15 is minus 25. 24 minus 25 is minus 1. So you end up with 39. Okay, so we have 2 pi times 39 over 60. Well, good news, 39 is divisible by 3. So we can say, okay, so that's the same as 2 pi times 13 over 20. You say, oh, well, wait, the 2 goes into 20. Okay, so that's the same as 13 pi over 10. And that seems pretty good place to stop. 13 pi over 10, and there we go, all fitting it nicely. We even fit it on the screen. Wow, amazing, amazing. Most of the work really is the setup, and the rest, just be patient, be careful, and check your work, right? All right, Well, we're doing great. Just a few problems left. Number 6. Consider a thin plate. Sometimes they call that a lamina, but that sounds very fancy, so we'll say thin plate, because that doesn't sound fancy. All right, so we have this thin plate, which is enclosed by the curves y equals square root of x and y equals x at the bottom in the first quadrant. And the thin plate has a density of square root of x. So in other words, as we move in the x direction, it gets thicker, right? So it's denser on the right than it is on the left. And what's the goal? Our goal is to find y bar, the y coordinate of the center of mass of the thin plate. All right, wow, this one's going to be a good workout. I can already tell. We haven't even started writing anything down. It's like, oh yeah, okay. Well, sometimes I like to save the best for last, right? We're not quite at that point, but we're getting close. Let's mark a couple things. First off, I think we can all agree this is at 0. So we see it goes here. How about over here? Where is that at? Well, when does x equal square root of x? Can you think of a value where that's true? Yeah, 0. Any others? 1. 0 and 1. These are, mathematicians love 0 and 1. And so when in doubt, say, well, I wonder if 0 or 1 works. And you're like, wow, it works surprisingly often. Okay, so that's good. We'll probably need some of those numbers as we go forward. Now, we're after our y bar, so it's good to take a moment and remember what's going on. So, how do you find y bar? Well, it's found by a ratio, namely a moment with respect to x and mass. And this is one of those weird things like, wait, what? That doesn't match, but it's done intentionally, and we'll get to why in a few moments as we go through and solve it. So we actually have to compute both of these values. We're going to divide, and out comes the answer. All right, so let's begin. Let's start by the mass, because that's a little bit easier to understand. Well, our mass is, we're going to add up our density and our area. And then we have a start and a stop. Okay, so that's how we go about finding mass. Density, area, added up. So essentially when we talk about a density, it's like mass per area. And so when we multiply it by an area, that becomes just a little piece of the mass, and you add them all together. Now the question, are we integrating with respect to x, or are we integrating with respect to y, and how do we know? Does it matter? Well, in this case, it will matter. We know definitively, 100% before we start, it's with respect to x. And you might say, how do we know 100%? Well, look at the density function. The density function is a function of x. Well, since the density is a function of x, that means we have to integrate with respect to x, because otherwise, hopeless. So we say, okay, so what's going to happen here? Well, let's start by figuring out our bounds. And we say, okay, where does our x go between? 0 and 1. So we say 0 to 1. What's our density? Well, now we take a thin slice, and our density of our thin slice is square root of x. That's the nice thing about taking a small slice. You say, oh, you treat your density like a constant. And so in this small piece, that's our density. Now, what's the area? Well, think of it as a rectangle. And as a rectangle goes, you say, well, I have a width and a height. Now the height, take top minus bottom. Square root of x is the top, x is the bottom. And now the width is dx. Okay, so area is height times width. Density. Yes? You see all those pieces? Yeah, sometimes, you know, if you look away for like 5 seconds, you're like, wait, what? How did that happen? All right, so we'll just remind ourselves where these pieces came from, because they will show up again. All right, now we have our integral, and let's go ahead and work this integral out. Okay, so this becomes our integral 0 to 1. We distribute, so that'll become x, and square root of x times x, we'll write that in a calculus-friendly way, x to the 3/2. All right, so that becomes 1/2 x squared, subtract, okay, add 1 to 3/2, that's 5/2, divide, so 2/5 x to the 5/2, and well, we need to evaluate from 0 to 1. Plug in 0, you get 0. So, okay, we'll plug in 1. So we get 1/2 minus 2/5. That's, common denominator would be 10. That's good, would be 5/10 minus 4/10, which is 1/10. All right, now, this is not our answer. This is the denominator. So we now know what m is. So what's next? We got to find our m sub x, which is our moment. All right, well, let's start going into that. So, next stage, mx. Now, what's the difference between a mass and a moment? Well, a moment takes into consideration distance. So when we're talking about finding a moment, we're adding up the little pieces of moment, which is going to be a distance times a density times an area. So again, the only difference is now we have a distance. And so for us, we have good news. We already know where we start, stop. We already know density. We already know area. So we need to talk about distance. All right. So this is one of our conversations where we're like, how do you find distance and what are we talking about distance for? So start with the subscript, the x in m sub x. That means we're taking the moment with respect to the x-axis. Because whenever you have a distance, you have to say, well, distance with respect to something. So with respect to the x-axis. Why with respect to the x-axis? Well, the answer is why. The reason we do it with respect to the x-axis is that the distance is measured by y. Essentially what's happening here is when you find y bar is you're averaging your y values based upon sort of how heavy your pieces are. So heavier pieces get more weight. All right, so now the question, what is the right distance? Well, is it the distance from the bottom? Is it the distance from the top? Or is it something else? And here's the part that you have to kind of remember. And the answer is, well, in this rectangle, because it's so small and thin, it's essentially a rectangle that's uniform. And if I have a uniform rectangle, so I really can't think of it like a rectangle, the center is in the middle. So the right distance is to the halfway mark. So that's the key. So this is the halfway mark down. All right, so when we go about setting up our distance here, well, how do you find the halfway? The answer is you take the bottom, you take the top, and you average. So the distance is going to be 1/2 of square root of x plus x. Okay, so here we go. We're having our moment is the integral from 0 to 1. We have 1/2 square root of x plus x times square root of x times square root of x minus x dx, right? Distance, density, area. Okay, now the good news is things are going to simplify. Well, we would certainly hope so at this point. And the reason is when you find this one, you'll notice you have something that looks like a plus b, a minus b. And because that's what you have. So what turns out to happen is you have the half, we'll have our density, square root of x, and then you'll get a squared, which is x, minus b squared, minus x squared. And sometimes this is the formula that they give you. They say, oh, it's 1/2 density f of x squared minus g of x squared. And you're like, what? Where did that come from? Well, what's happening, of course, is you're combining pieces about area and distance. And so if you can memorize formulas, great. But if you're getting a little bit gray in the beard, maybe just don't try to memorize too many formulas. Just say, look, we'll figure it out. We know how to set things up. We're pretty good. I mean, we're in Calc 2, right? We're pretty smart people. All right, we got to finish this, right? We want to make sure we finish under our time. Okay, so that's integral 0 to 1. We're going to distribute through 1/2 x to the 3/2, right? 1/2 plus 1 minus x, then 2 plus 1/2. Well, that's 5/2. All right. So we have 1/2, and then we're going to add 1, that's 5/2, multiply 2/5. And then add 1, 7/2, multiply 2/7. Okay. Good. Evaluate 0 to 1. Now the nice thing is you plug in 0, you still get 0. 0, our friend. And so we plug in 1. So we have 1/2. Well, actually, let's just go ahead and see how we have a half and 2's and 2's. So we can just... So we really have what? 1/5 minus 1/7. That's in the end, that's what it simplifies to. All right, well, that's 7 over 35 minus 5 over 35, common denominator being 5 times 7, which is 2 over 35. All right, good. And now we're ready. What's our last thing to do? Well, remember, this, again, is not our answer. So what we've been finding, we found m, we found m sub x. So our last thing is we say, all right, y bar, which is m sub x over m, well, that's 2 over 35 divided by 1 over 10. Okay, well, we can clean that fraction up. That's the same as 35 over 2. Whoops. No, sorry. I thought that was downstairs. That's why I wrote 35 over 2. Pay attention, especially on a test, There's something that happens that towards the end of a test, like your brain starts like, okay, 2 over 35, and then this is what gets flipped over, 10 over 1. And, all right, what can you do? Well, 35 and 10 have a common factor of 5. So if you pull that out, you'll get 2 times 2, which is 4 over 7. 4/7. And there's the answer, 4/7. Now, is it reasonable? Well, 4/7 is what? It's pretty close to halfway, and yeah, that seems about reasonable. If the answer had been like 1.5, mistakes were made. If the answer was negative, mistakes were made. If the answer were 0, or you want it to be a reasonable thing, because you can kind of eyeball and say, yeah, about middle seems right. So it doesn't hurt to be like, let me just, if nothing else, is this a reasonable answer? But there we go, 4/7. All right, good. And I think we have one more problem to go. Our final problem. Woohoo! Yes! We've made it to the end. All right. Well, let's not party yet. We still want to make sure we do all the problems, because it's better to get as many points as we can on every exam. So, find the area A lying inside the polar curve r equals 2 minus cosine theta and outside the polar curve, r equals 3 plus cosine theta. And it's shaded in the graph. So yeah, it's another problem that you could say, this one seems a bit shady. But, all right, anyways, what do we have? Well, we have our two curves, and we can say that this curve, that's the 2 minus cosine theta, and that curve is the 3 plus cosine theta. And if you're wondering, like, well, how can you say that so quickly? Well, because I can see that I'm inside this one, and I'm outside that one. So I'm just using the information given. All right, now, what do you do for a polar problem? When it's an area, we need to remember our basic setup. So area, the way area works, it's kind of interesting. What you do is you basically add up sort of wedges, and almost like slices of pie, and you put them together. So you have a start and a stop, alpha and beta, and then it's 1/2, and then you're going to do the outer part squared minus the inner part squared, and then you have your d theta. All right, so that's our basic formula, and that's just a good one to know. And of course, the 1/2, well, that's easy to forget, so don't forget that. All right, well, what do we need? Well, we need to know our start and our stop. Now, part of it is we can look at our figure and say, oh, we have symmetry, so we can do the following. Say, look, let's just cut it in half. And in that case, we can say, look, we'll stop over here at pi. Because if you think about your coordinate system, right, 0, pi, and then you have this angle. All right, well, let's work through what that needs to be. So to figure out, we say, when does 2 minus cosine theta equal 3 plus cosine theta? Well, the good news is we can move things around, and this is the same as minus 1 equals 2 cosine theta, or cosine theta is minus 1/2. And you start thinking about, okay, what angles do that? And you might say, well, I remember that cosine of 60 degrees, that's a positive 1/2. And so it's this angle is like a 60-degree angle here. And it matches the picture, right? You kind of know, like 30, 45, 60, right? 45 is exactly in between. 30 is below 45, 60 is above 45. So yeah, this looks like the 60-degree angle. You're going to get usually pretty common angles. And so you say, okay, so that's probably, all right, so if that's 60, then if I do 180 minus 60, that's 120. But we don't use 120 because we're in calculus. We're radian people when we're in calculus. And so we say, oh, so that would be 2 pi thirds. All right, so here we go. Let's start setting up our integral. So our area, we're going to go from 2 pi thirds to pi. Because we're only going to do half of it, we're going to double, right? Because we're finding this part. So we're going to find that part and double it. So that's why there's a factor of 2. Then we have 1/2. And now we have to talk about outer versus inner. Now the way you do this is, it's very simple. Remember that polar, everything comes out of the origin. It's the pole. And how do you relate to the origin? So the outer would be, if you went from the origin, what's the last curve you hit, or the farthest out? Well, it's the 2 minus cosine theta. So 2 minus cosine theta squared. The inner is the first time you hit. So outer, far away, inner, nearby. So that's the 3 plus cosine theta squared. And there we go. We're good to go. And now it's just a matter of working it through. So the 2 and the half cancel. Nice. And what else can we do? Well, we can do the following, of course, which is to expand. All right, so 2 minus cosine theta squared, that would be a squared for 2ab. So it would be 2 times cosine theta. And don't forget the minus, so minus 4 cosine theta. And then plus cosine squared theta. All right, so that's the first term squared. Subtract, okay, do it again. A squared, 9, 2ab. Don't forget the 2 in the middle. That's an easy thing for us to forget. So 2 times 3 times cosine theta would be 6 cosine theta. And I'm writing it as plus 6 because I've used parentheses. Parentheses are really good, especially whenever you have a minus sign, because it's really easy to forget them. And when you forget a parenthesis, mistakes follow. And we don't want to make mistakes. We just want to get the right answers. We love right answers. They tend to get more points. All right, now, what do we have? 2 pi over 3 pi. We have 4, subtract 9. That's negative 5. Minus 4, minus 6. So that's minus 10 cosine theta. Cosine squared minus cosine squared is 0. Now, at this point, you're probably getting a little bit nervous saying, these are negatives. How can an area be negative? Oh no, did we make a mistake? No, we did not. We are fine. It only looks negative, but the thing is, in the range from 2 pi over 3 to pi, cosine theta is negative, and in particular, this whole expression is actually positive. So it only looks negative. So don't panic, but it's okay to be a little skeptical, just a little bit. All right, well, okay. From here, we're ready to integrate. Isn't it cool? See the cosine squareds? And we're like, oh, power reduction. And I was like, oh, it worked. They vanished. Nice. Because, well, you know, our Calc teachers, they love us. They pretend like they don't love us, but come on. We know there's a lot of love in their hearts. All right, so let's keep going. We're through the hard part, I hope. So we have minus 5 theta. Integral of cosine is sine. So minus 10 sine theta. And we're going to evaluate from 2 pi over 3 all the way up to pi. All right, so we'll have a minus 5 pi, and then minus 10 sine of pi. The sine of pi is 0. So that's the first thing. Subtract. Okay, plug in 2 pi over 3. So we're going to have minus 10 pi over 3. All right, 5 times 2 pi over 3. And then subtract 10. And we have to think about sine of 2 pi over 3. So when we came up here, we said that this point, maybe we'll redraw it. So this angle here, we saw that the cosine value was minus a half. Can we find the sine value? Well, the answer is yes, right? Because a squared plus b squared is 1. Cosine squared plus sine squared is 1. So what's the sine value? It is square root of 3 over 2. All right, so we're going to have 10 times the square root of 3 over 2. All right, well, this minus comes in and becomes everything plus. 10 over 2 becomes 5. So this becomes 5 square root of 3. That's good. That's a positive thing. And then here, well, we have a 5 pi is common to both. So I'll factor that out. We have 5 pi. And if we do that, we'll have minus 1. And here, what do we have to multiply by? Well, we need to multiply it by 2/3. So minus 1 plus 2/3. And so this gives us a final answer of 5 square root of 3. Minus 1 plus 2/3 is minus 1/3. So minus 5 over 3 times pi. And we're done. We're done. And we made it. All right. Way to go. You can do this. You can do this. And the nice thing is when you're taking the test, you don't have to explain everything. And oftentimes that's what we're spending a lot of time on. So don't panic. You'll be fine. I believe in you. And that's coming from me, your friend, Reginald Q. Picklebottom himself. All right. Take care.